Okay, hello everybody. Thank you for joining the webinar, and let's go ahead and get started. My name is Mark Bollinger, and I'm a research scientist at the Lawrence Berkeley National Laboratory. And today I will run through findings from an article that we recently published in the IEEE Journal of Photovoltaics titled Land Requirements for Utility Scale PV, an empirical update on power and energy density. And you can download a free copy of this article from either of the websites shown on this title slide. As you probably just heard, we are recording today's webinar, and we'll post it at the second website listed on this slide. And we will try to get that up posted by tomorrow, which of course is Groundhog Day, just in case any of you mysteriously feel the need to watch it over and over and over again. Finally, we're aiming for just a half hour today, so I will be moving through this fairly quickly, but I do hope to leave a few minutes for Q&A at the end. So if you have any questions, please use Zoom's Q&A feature to type them in, and I will do my best to answer as many as possible. So let's begin by briefly reviewing what power and energy density are and why they matter. Power density is a measure of how much generating capacity of a given resource, in this case solar, fits into a given land area, and we express solar's power density in terms of megawatts of DC capacity per acre. Energy density, meanwhile, measures how much electricity that resource can generate per unit area, and we express energy density in terms of megawatt hours per year per acre. Now, the power and energy density of solar matter because virtually all modeling studies looking at decarbonization scenarios tell us that we're going to need to build massive amounts of solar in order to decarbonize not only the power sector, but also the broader economy. And this in turn means that the amount of land occupied by utility scale PV plants will continue to grow, most likely at an accelerating pace, thereby heightening and potentially exacerbating concerns about the overall land requirements and associated land use impacts of that build out. The amount of land required to build a utility scale PV plant is also an important cost consideration. And unlike many of the other cost components of a PV plant, which tend to decline with greater deployment through learning by doing, the cost of land will instead most likely increase with greater deployment as competition for good sites heats up. Because as either Will Rogers or Mark Twain, or maybe both, once famously quipped, land is the one thing that they ain't making any more of. And while there are potentially other ways, such as agrivoltaics, to mitigate some of utility scale solar's negative land use impacts, really the only option available to hedge against rising land costs is to increase the power and energy density of PV plants. So power and energy density matter from both a land use and a cost perspective. Unfortunately, the last major study of utility scale PV's power and energy density is now almost a decade out of date. Specifically, NREL published a report on this topic back in 2013, back when the utility scale PV sector was still quite young. And that early report is still routinely cited on issues related to power and energy density. This despite the fact that it's now nearly a decade later and a lot has changed in that decade. Most notably, module conversion efficiencies have steadily increased and can be seen via ever higher module wattages. Mounting preferences have largely shifted away from fixed tilt racking in favor of single axis tracking in most parts of the country. And the tracking algorithms themselves have become more sophisticated over time, helping to boost energy capture. So in light of all of these changes and with growing concerns over land use, we figured it was high time for an update of solar's power and energy density. And that's what we've now provided with this newly published article. So here's what we did. First, we relied on plant level data from a separate Berkeley Lab product, namely our annual utility scale solar report series, to define the universe of utility scale PV plants in the US that are ground mounted and larger than 5 megawatts of AC capacity. We also pulled relevant metadata for each plant from that same report data set. Next, we used ArcGIS to draw polygons around each of those utility scale PV plants and to calculate the area within those polygons. And then finally, we calculated both the power and energy density of each plant and then analyzed geospatial and temporal trends across plants. And here are a few examples of what these plants and our polygons around them look like. So in the upper left is the kind of site that developers no doubt dream of, where it's possible to completely fill a flat parcel of land with a perfectly square array of trackers. So that's perhaps the ideal, but as we see in the other two examples, reality often gets in the way, whether it's in the form of an existing building, like we see here in the middle image, or maybe a pronounced drainage area like we see over in the right-hand example. Here are just a few more examples. Down in the bottom left, we see a big plant in California that is broken up into many different arrays by various land features. In the middle, there's a South Carolina plant that looks like it might be spanning several contiguous lots. And then in the upper right, there is a tracking plant that seems to be on a commercial lot that also includes a large building. In all of these examples, you may have noticed that we've drawn the polygons to include only the area that is directly occupied by the array or the arrays of modules. And we've done it this way for two reasons. First, and most importantly, site boundaries are almost never visible from satellite imagery. So for example, in the image of the California plant down in the lower left portion of this slide, it's really hard to envision where the overall site boundaries might lie. But in contrast, it's very easy to see where the arrays themselves are located. So that's the main reason. But second, even if we knew the site boundaries, it's not clear what good that information would actually do us. And the example that we use in the paper to make this point is the Copper Mountain 3 project in Nevada, as shown on this next slide. So here in this example, the red polygons measure the direct array area, which is 945 acres. And the yellow polygon, which I very roughly sketched in based on a map obtained from the lessor, measures 1,375 acres. So in this case, the array occupies only 69% of the total leased area, and the shape of the total site or the total leased area seemingly has relatively little bearing on the shape of the array itself. In other words, both the shape and the acreage of the total site tell us very little about the actual power and energy density of the plant. Moreover, this relationship between array area and total site area could conceivably vary quite a bit from plant to plant, depending on what your site looks like, which makes it hard to generalize any useful metrics or rules of thumb across plants. So in the end, we measure only the area directly occupied by the array, as that seems to provide the most information content in terms of density, and also seems to be the only consistent approach across different plants. And what this means is that you may need to adjust our densities accordingly if you are interested in how much PV you can fit on a particular parcel of land. So for example, if you can only build on 75% of your site due to wetland issues or what have you, then simply multiply our densities by 75%, and that should get you pretty close to the right number. Okay, here is a tabular overview of our sample. The left side of the table shows all plants, and then to the right, we break down the overall sample into fixed tilt and tracking plants. Overall, the sample includes 736 operating plants, totaling 35.5 gigawatts of DC capacity that came online across 38 states between 2007 and 2019. So this is a sizable sample that represents more than 90% of all utility scale PV plants built over this period. But as shown by the red shaded triangle, or I'm sorry, red shaded rectangle up in the table, the sample size in the first few years is pretty small, reflecting the sector's youth and slow gradual build out at that time. So because of that, we've chosen to start our analysis in 2011 rather than back in 2007. And here we see a graphical overview of the sample. So starting with the graph in the upper left, we see that by the end of 2019, there were nearly twice as many tracking plants and twice as much tracking capacity as fixed tilt within our sample. And this divergence has really only developed since 2015 and mostly reflects the declining cost and increasing reliability of single axis tracking. To the right of that graph, we see that module capacity has increased significantly since 2011, again, driven by increasing conversion efficiencies. And we also see that the early tracking plants tended to use higher powered modules than the early fixed tilt plants, presumably as a way to wring the most value out of what was back then at the time an expensive tracking system. On the bottom left, we see that both fixed tilt and tracking plants have migrated to less sunny parts of the US over time as costs have come down, but that the median tracking plant has regularly been built at sunnier sites than the median fixed tilt plant, which makes sense. And then finally, in the graph on the bottom right, we see that since 2014, fixed tilt plants have increasingly been relegated to higher latitude sites as tracking continues to make inroads across the country. And you'll see some of these trends reflected in the density results, which we will turn to now, starting with power density. So sticking with our color scheme, everything shown here in blue pertains to fixed tilt plants, while orange denotes tracking plants. For both types of mounts, both fixed tilt and tracking, the solid line shows the median power density over time, while the shading around that median shows the 25th to 75th percentile range. The dashed lines that you see there show the influence of module wattage on power density, and the two circles back in 2012 show estimates from the 2013 NREL paper, included here really just for reference. So two aspects of this graph likely jump out at you. First, you'll notice that fixed tilt plants shown in blue consistently have higher power densities than the tracking plants shown in orange. This is because fixed tilt plants typically have a higher ground coverage ratio, and ground coverage ratio is simply a measure of how tightly the modules are packed into a given area. Because fixed tilt modules are by definition stationary, there's less concern about self-shading in the mornings and evenings than you would have with a tracking plant, which allows for tighter row spacing and thus a higher ground coverage ratio, which in turn translates directly into a higher power density. The second thing you'll notice is that over this period, the median power density has steadily increased by 52% for fixed tilt plants and by 43% for tracking plants. This improvement was driven primarily by the increase in module efficiency and wattage that we saw on the prior slide and that you can see again here reflected in the dashed lines. But other factors have contributed as well, such as improvements to tracking algorithms and things like plant design software, all of which can enable higher ground coverage ratios. Okay, here we see the corresponding graph for energy density. Whereas the prior slide showed that fixed tilt plants typically have higher power densities than tracking plants, when it comes to energy density, it's more of a toss-up due to tracking's greater production per megawatt or greater megawatt hours per megawatt. For example, here we see that the respective energy densities of fixed tilt and tracking plants largely overlap until about 2015, at which point there is a notable divergence, which can be explained mostly by the relative migration of single axis tracking to less sunny parts of the US. So in other words, as the incremental cost of trackers has diminished and the product has improved, tracking has been deployed more widely throughout the US and no longer only at the sunniest sites. And that trend is borne out by the thin dashed lines, which in this case reflects trends in site resource quality. And because our medians reflect national numbers, this migration out of the Southwest and into less sunny parts of the country means that the increase in energy density has not quite kept pace with the growth that we saw in power density. Specifically, energy density has increased by 33% for fixed tilt plants and by 25% for tracking plants. So far, I have focused on temporal trends in the medians, but there's clearly a range around those medians as well. And that range depends at least in part on geospatial factors like site latitude and irradiance, which of course are somewhat related. So here we see two scatter plots that compare power density versus latitude in the top graph and energy density versus site quality in the bottom graph. And here we're looking at only the most recent plants in our sample. So in other words, we've taken time out of the picture in this case. We're just looking at the most recent projects. So up top, we see that the power density of fixed tilt plants declines at higher latitudes, which makes intuitive sense given the need to space rows farther apart at higher latitudes in order to avoid self-shading as the sun is lower in the sky. For tracking plants, the relationship with latitude is less obvious, and quite frankly, it's probably not very meaningful. Keep in mind that for tracking plants, the rows run north to south with the modules tracking east to west, which means that self-shading at higher latitudes is really less of an issue or not much of an issue for tracking plants in the same way that it is for fixed tilt plants where the rows run east to west with the modules tilted south. In the bottom graph, we see that energy density increases at sunnier sites for both fixed tilt and tracking plants. And this, of course, makes intuitive sense as well. So really the point of these graphs is to look at some of the variation around the medians that we'd shown in the prior two graphs. So let me briefly wrap up here. Though I haven't yet mentioned this, I'll just note here that our power and energy density estimates from the early years do match up pretty well with the often cited NREL numbers for fixed tilt plants, but not as much for tracking plants where the NREL numbers look to be a little bit low. Since those early days, both power and energy density have increased significantly, with power densities up 54% for fixed tilt and 43% for tracking, while energy density has increased by 33% and 25% respectively. And what this means is that anyone who's been relying on the outdated density estimates from that earlier NREL report has been significantly overstating the land requirements of utility scale PV, and by extension, perhaps also the land use impacts. Within the blue shaded rectangle that you see here, I provided updated reference densities for 2019, which will ideally replace the outdated NREL numbers that are often still used. Again, these numbers represent the area directly occupied by the array and not the total site area. And then finally, I will leave you with some next steps. The first of which is to hopefully update the analysis through 2021 and then ideally future years as well, so that these benchmarks of solar's power and energy density never become as stale as they were prior to this update. And when conducting those future updates, we should also keep an eye out for the impact of the new, larger format, higher powered modules, as well as bifacial modules, both of which could increase at least energy density, if not also power density. Because our plant sample only ran through 2019, we really didn't have any of these newer types of modules in the sample to any measurable extent. And along these same lines, the emergence of hybrid PV plants with DC coupled battery storage is perhaps another thing to keep an eye on, as DC coupled storage could effectively increase solar's energy density by capturing generation that would otherwise be clipped and therefore wasted. So there are a few innovations kind of coming through the pipeline here that could have a significant impact on solar's power and energy density. So it is important to keep an eye on this going forward and to update this study as frequently as possible. Okay, so that's all I have for the presentation, and it looks like we do have actually quite a bit of time for some questions. So let me see if I can pull up the Q&A here and and start going through your questions. Okay, someone asked if it's possible to shrink the slide font and format. I'm obviously seeing that one too late. I apologize. Someone else answered, someone else asked, I'm sorry, is it fair to say full site boundaries are important if we are interested in habitat fragmentation? I think the answer to that is probably yes. Basically, what we were tracing with our polygons is kind of the permanently disturbed area of the site, but obviously during construction, Some of the surrounding area also gets at least temporarily disturbed. And as the questioner notes, there's also an element of habitat fragmentation there that is important. So yes, I think for that specific purpose, it is important to be looking at the full site boundaries. Okay, someone else asked whether I can share the median module wattage used to develop the energy density calculation. Yeah, so let me just talk about how we calculated energy density. So there, what we did is we actually took the empirical capacity factor of each plant, averaged over as many operational years or full calendar years of operations exist for that plant in question. And so that is giving us our megawatt hour number. I'm sorry, megawatt hour per year number. And then the acreage just comes from the polygon. So the module wattage actually does not enter into the energy density calculation. It is a driver of increased energy density as well as power density as module wattage increases, but it's not entering directly into that calculation. And I did show a slide which kind of shows the median module wattage over time within our sample for both fixed tilt and tracking plants. So I would, I guess, refer the questioner to those particular graphs. Okay, someone else asked, is energy density also driven by changing loading ratios of PV to inverters? Yeah, so this is an interesting question. We expressed our power density in terms of DC capacity, so megawatts of DC capacity per acre. You can also do it in terms of AC capacity. We chose not to do that simply because of this issue about loading ratios or DC to AC ratios and how those have moved around over time. So one way to think of it is you could have a 100 megawatt AC plant, but the DC capacity associated with that 100 megawatt AC plant, could range anywhere from just 110 megawatts of DC all the way up to, 150 megawatts of DC, or perhaps if you've attached a DC coupled battery, you could even go all the way up to, 200 megawatts of DC capacity or higher. And obviously, in that case, the power density of that plant in AC terms would not change with the different loading ratios, but obviously 200 megawatts of DC capacity is going to take up a lot more land area than 110 megawatts of DC capacity. And so your densities when expressed in DC capacity do actually pick up that change. So that's why we decided to look at things in terms of DC capacity. But the questioner is correct that you would see a different trend if we were doing this in terms of AC capacity. In general, because the DC to AC loading ratio has increased or drifted upwards over time, we would expect to see probably a lower improvement in power density if expressed in AC capacity terms. So hopefully that answers your question. Let's see what else we've got here. Someone asked if we are considering a similar study for hybrid resources, especially since it is growing rapidly. I would say that that is not in the works, but I will say that we do have a kind of a separate tracking effort where we try to gather information as all kinds of metadata on the various hybrid plants that are both coming online and in the pipeline. So this is certainly something that we could look at. And as I sort of implied, DC coupled storage could be an interesting way to actually boost the energy density of utility scale PV a little bit further. So that is something that we're keeping an eye on, but no concrete plans for a similar study at this point. Okay, someone asked whether we have any extrapolations to community scale solar, which are smaller plants, generally up to 2 megawatts that are interconnected at the distribution level. And the answer there is yes, actually. Well, let me rephrase that. I don't necessarily have any extrapolations, but I do have some colleagues who are working on doing similar types of things with polygons, extending the size range down to 1 megawatt. So within their sample, many of these community scale plants would definitely show up. And I'm not quite sure of the timing of their work, but I think there probably will be something coming out on that over the coming year or two. Someone asked whether we foresee a continued increase in the power and energy density over the next several years. And, I guess I'm more optimistic on energy density than power density. I mean, certainly like for bifacial modules, all else equal, all else being equal, it may not impact your power density to any great extent, but with added production from the backside, that could theoretically boost your energy density going forward. So that coupled with the DC storage, coupled with the larger format modules, yes, we could certainly see further improvements going forward. And of course, the efficiency of modules will no doubt continue to improve as well. Scrolling through here. Okay. So someone asked, why would any project developer use a tracking system instead of fixed tilt, since both power and energy densities are higher for fixed tilt systems? Yeah, so that's a great question. And the answer is simply cost. So, it's true that your typical fixed tilt plant has a higher power density than tracking plants, just simply due to the higher ground coverage ratio, as I mentioned. In energy density terms, it tends to be more of a wash, but even so, the energy densities of fixed tilt and tracking are not too dissimilar. But the reason you still want to go with tracking is because you're achieving that energy density with less capacity. So, because the tracking plants generate more megawatt hours for each megawatt, you're able to achieve that higher energy density using fewer modules. And because modules are costly, if you can reduce the amount of capacity in the plant or the number of modules, you're better off on a levelized cost of energy basis. So that's really the reason. I didn't bring cost into this presentation, but it is sort of the missing ingredient here. Okay, someone asked if we determined optimal ground coverage ratios for tracking and fixed tilt systems as part of this analysis, or did we see any trends for typical optimal values? And the answer there is no. We did not get down to that level of detail. Again, we're working with satellite imagery, which doesn't necessarily allow for that refined of an analysis. It is something that we obviously considered when trying to make sense of these trends that we were seeing, but there was no optimizing done. Let's see. Someone else asked if we have published or will publish data tables from this study that include some of the underlying data. And the answer there is, this is something that we're hoping to make public going forward. We haven't done so yet. As I mentioned earlier, I do have some colleagues who are working on expanding the data set. And I think once we get a little further along with that, we will try to make as much of this public as we can. And with that, we are now at the half hour. So again, I want to thank everyone for showing up. I want to thank the U.S. Department of Energy for funding this work, and also thank you for all of the great questions. So with that, I guess have a great rest of your day. If I haven't been able to answer your question, I will attempt to get back to you via email. Thank you, everyone. Enjoy the rest of your day.